All right. So today we're going to talk about symbol grounding, as Paula was just mentioning. I prepared a pretty long lecture. I hope I make it through it. I'll try and emphasize the parts that I think are most important. You'll see that a lot of the slides are wordier than the ones I usually prepare, and that's because there's a lot of philosophical content here, a lot of stuff to think about, and kind of have to be precise when you talk about them. But the overview is more or less what we see here, three main parts. First, an introduction. I'm going to try and spend a lot of time here at the beginning because this is where we see the basics of symbolic versus non-symbolic or connectional systems. There's a thought experiment, a very famous one called Searle's Chinese Room. And then the definition of what the symbol grounding problem is and what the relevance is of all this philosophical talk that we have. We're going to see that it pops up quite naturally. Then there's this big chunk of content that is following a research summary from a few years ago that overviews around 8 proposals for solving the symbol grounding problem. And then we can quickly see, based on all of this introductory material, why they don't work. And then some closing remarks, some proposed set of requirements that we can see that that would be necessary for arriving at a solution for the symbol grounding problem, and just then a little bit of discussion and what the relevance is to the course. Right, diving right in then, we're going to start with this dichotomy of symbolic versus non-symbolic systems. So, AI was born in the 1950s from computer science, math, and logic. One of the main ideas behind this endeavor was to automatize human intelligence. Of course, it's not necessarily human intelligence that we're after, but it's the only real intelligence at a high level that we know about in the world, so it's a good guiding light. So reasoning and learning are identified early on as 2 pillars of AI. So the cognitive approach posed this symbolic model of the mind where, essentially we have a symbol system, and cognition is simply or not simply symbol manipulation. On the other side, we see that connectionist or non-symbolic or sub-symbolic group of people or camp proposed a competing view based mostly on an empirical perspective, which is, very, very close to the data or what in this course we're calling perceptual data. We'll see that apart from these, huge branches of knowledge, computer science, math, and logic, we have psychology also and cognitive science. They have a lot to say, and of course, philosophy, which is the mother of all knowledge. So in this first part, I'm going to follow Harnad, which is the seminal paper on the symbol grounding problem, a 1990 paper. We'll see that there's quite a bit of stuff on machine learning that was already around at that time. So for those of you who thought that this is newfangled stuff, we'll soon see that it's been around for some time. So a definition of a symbol system is not that easy to arrive at. We're going to follow Harnad's definition and see that we have quite a few requirements. First of all, we have a set of arbitrary physical tokens, which the tokens can be anything: scratched on paper, hole on tape, or punching a punch card, events in a digital computer nowadays, of course, that are manipulated on the basis of some set of explicit rules. And these rules are in themselves physical tokens and strings of tokens. They have to be specified somehow. And this symbol token manipulation is based purely on the shape of the symbol tokens, not their meaning. We're going to delve into what that means in a bit. So it's purely syntactic. That's the way to think about it. And there's a combination, rulefully or based on rules, that combine and recombine symbol tokens. Following more requirements, there's a primitive atomic symbol tokens and a set of primitive atomic symbol tokens and composite symbol token strings. So the entire system and all its parts, so the atomic tokens, the composite tokens, all the syntactic manipulations, both the actual and whatever is possible, are all semantically interpretable. So here's where we arrive at this issue where we're going to see that we run into a little bit of a problem. So syntax can be systematically assigned a meaning. This is what we refer to. So there's the token will stand for some object, it will describe some state of affairs, some relationship, and so on. If we look at these 8 conditions or properties, they all seem to be critical to the definition of symbolic. So weakening or eliminating any of them causes this, what Harnaud calls a natural category to fade for one of 2 reasons. Either the links with formal theory of computation are severed somehow, if you eliminate the rules or the principled manipulation, or this is the most interesting and philosophical thing, only unexplained metaphors remain that differ from speaker to speaker. So it's very important for this to be not centered on one speaker, but it has to be really useful in communicating concepts across agents, not just one. On the other side, we have connectionism or subsymbolic systems. So again, this is following Harnaud. Already in 1990, we had, of course, neural networks. They had been around for some time, parallel distributed systems, and other subsymbolic systems, some bio-inspired systems. And even though, especially because of this last category, even though this class is often compared to the brain, the resemblance or lack thereof is really beside the point for our purposes, so we won't go into that. But there are formal principles underlying connectionism, and they are based on associative and statistical structures, so causal interactions, between, for instance, neurons or nodes in a neural network. A neural network is just one possible implementation. Usually when we hear connectionism, we see that it is very closely related to neural networks, but it's not the only mogel. So according to connectionism, it's quite opposite to symbolic systems, where here cognition is not symbol manipulation, but rather dynamic patterns of activity in some sort of network, a multi-layered network nowadays, a deep network usually for deep learning, where we have nodes, units with weighted, positive and negative interconnections, and whatever functions that we want to implement with these models arises or emerges from this activity. And the patterns can change so learning goes on when patterns change according to constraints that govern how activations and connection strengths are adjusted. So essentially, if the basic backpropagation algorithm, what I'm talking about. Things get adjusted, and the result is a system that learns, recognizes all sorts of patterns, solves all sorts of problems, and can even here, this even kind of is evidence that we're, in 1990 terms, exhibit motor skills. Nowadays, exhibiting motor skills is quite common. We have self-driving cars that are doing quite well out there on the roads. And there has been some disagreement regarding whether or not connectionism is actually a subclass of symbolic system. We won't go into this. But if we go back to those 8 criteria, we see that they're not all there really. So an example application here, for those of you who don't know who this is Leo Messi, a player in Argentina. We can see a connectionist system that can easily nowadays recognize his face. can have some output, Leo Messi. You can have some other things going on here. We can look at the jersey, the crest on the jersey says that it's the Argentine national team, and the fact that gold symbol there on the chest means that Argentina won the World Cup. So this is a kind of things that we can pick up from perceptual data nowadays quite easily. But we can see that the system is correctly identifying the player in the photo and all of those properties that we saw. But this is simply a label, like we were saying before, a scratch on a paper or some sort of token that is applied to some part of the photo. So, you can see the outline there being applied. And even though other labels may be applied, like we saw before, purely connectionist systems are somewhat limited. So, for instance, they can't know, with scare quotes there, anything about the perceptual data they work with. So in the case of Leo here, apart from being a person, because maybe it's this label belongs to a set of people or players. You see a player, a coach, a fan. What is he? So these systems need to be trained on large sets of data, and of course, as you've probably seen, they can be easily fooled by adversarial noise. So let's see the same sort of example on the symbolic side. So consider the following set of first-order logic, rules or formula. You can see, the typical ontological kind of thing going on here, where we see that every soccer player is a person. If we have the plays for relation, the first position here is a soccer player. In this case, if two players play for the same team, they are teammates. In this case, Leo is a soccer player, plays for Argentina, and another player, in this case, Di Maria, plays also for Argentina. So, I went through these 6 formula quite easily. You understood it immediately. This is a knowledge base that is quite easy to understand. It's also quite easy to see what the consequences or the inferences are from these formulas. So, we have Leo is a soccer player, then Leo, of course, is a person, and so on and so forth. But let me do this quick experiment with you. What if I do this? For a non-human agent, they're going to see something more like this, right? They're going to understand what for all means. Of course, there'll be these tokens, X, whatever, but then these roles and the relations, they're not clear at all what they mean. It's like if I just said this to you, you wouldn't have basically no idea what you're talking about, what I'm talking about. So suddenly the symbol system's advantages that we were touting and so proud of seem to be tied to their ability to connect to the domain they are designed to function in, right? And this can be seen as Harnad proposes or calls it a severe handicap that has been noticed, even before Harnad in various forms since the advent of computing way back in the mid 20th century. So this is what Harnad dubbed the symbol grounding problem. So why is the need to establish a connection such a handicap? It's maybe not that big of a deal. So it can be argued that this connection is what lies at the heart of, the secret sauce behind our intelligence. And without a clear understanding of what role it plays and how to produce it, then we really cannot develop truly intelligent systems. So whatever this means, but something will always be missing. Well, as we're going to see during this lecture, there's always some sort of helping hand from the outside that's solving some sort of a problem for you. So the thought experiment that in 1980 the philosopher John Searle proposed is quite interesting to see what we're talking about specifically when we refer to this handicap and this limitation in symbolic systems. So the Chinese room argument, it's a challenge that to this idea that generating behavior that is indistinguishable from a person then this means that we have an agent that has a mind or is intelligent, as Turing proposed in his Turing test. So the experiment is quite simple to imagine. So Searle imagines himself, he puts himself in a room following some computer program or a big set of rules for responding to Chinese characters that are slipped under the door. So somebody is feeding from the outside of the room some Chinese characters on a sheet of paper. Searle understands nothing of Chinese. That's why he chose this language. And yet, if he follows these sets of rules, these programs for manipulating symbols and numerals, just as the computer does, this is why he proposes this scenario, he sends back appropriate strings of Chinese characters out under the door. And this leads those outside to mistakenly suppose that there's a Chinese speaker in the room. So of course, this is a pretty thinly veiled metaphor for what a computer is, right? There's somebody's or something in there just following instructions. If we can just talk to it and it'll give back reasonable responses, can we really think that there's an intelligent person in there? Nowadays, with ChatGPT and these other LLMs, it's quite easy to actually think about this as actually happening. When Searle proposed this in 1980, this was pretty far from being a reality. So the conclusion is that since really no part of the system understands Chinese, really not the rules, not the person, then the system as a whole does not either. So the symbols and their manipulation, they're all based on shape, syntax, rather than meaning. So they are systematically interpretable as having meaning, and that's what it means to be a symbol system. But however, the interpretation cannot be intrinsic to the symbol system itself. It will be what Harnaud calls parasitic on the fact that the symbols have meaning for us. So if the meanings of symbols in a symbol system are extrinsic rather than intrinsic, like the meanings in our heads, then they are not a viable model for the meanings in our heads. And the conclusion of this Chinese room argument is that cognition cannot be just symbol manipulation. So that's basically the philosophical argument behind this, the fact that the disconnect between symbols and meaning is really a severe handicap for symbolic artificial intelligence. So the symbol grounding problem then is essentially proposed in this way. So symbols constitute a symbolic system without causal links or resemblance to their corresponding meanings. So they are merely part of a formal notational convention. So Harnaud proposes this, the SGP in this sense. So how can the semantic interpretation of a formal symbol system be made intrinsic to the system? So, make it be really, really autonomous rather than just parasitic on the meanings in our heads. How can the meanings of the meaningless symbol tokens, as we saw in the example with the soccer players, manipulated solely on the basis of their arbitrary shapes, be grounded in anything but other meaningless symbols? So that's essentially the proposal of the symbol grounding problem, as I mentioned in the introduction, following this paper by Taddeo and Floridi in 2005, Solving the Symbol Grounding Problem, a critical review of 15 years of research proposed in up to 2005. And then we'll see a few other works if we have time. We're going to see a few strategies that will illustrate what the efforts have been to come up with solutions to this problem. And as I already said, why they don't work. So we're going to see three main approaches based on the level of representation that they assume. And all approaches seek to ground symbols through what are called sensor-motor capacities of the artificial agents involved. So unfortunately, all strategies turn out to be semantically committed. So this means that they're making somewhere in there's a hidden assumption or a helping hand, like I said a while back, and hence none of them really offer a valid solution to the SGP. So before going forward with these 8 strategies, we first discuss a basic condition that is necessary to address the SGP, and we're going to see a little bit more about what role the philosophy plays in this endeavor. So this condition is called the zero semantical commitment condition. So the symbol grounding problem concerns the possibility of specifying precisely how an autonomous agent, from now on, I'll just say AA following Taddeo and Floridi, can elaborate its own semantics for the symbols that it manipulates, and do so from scratch. This is the key issue that we need to make sure is true, by interacting with the environment and with other agents. So what follows from this is that no form of innatism is allowed. So no semantic resources, or in Latin, some virtus semantica, should be presupposed as already pre-installed. Otherwise, we're just, we're cheating. On the other hand, no form of externalism is allowed either. So no semantic resources should be uploaded from the outside, or some deus ex machina already semantically proficient helping us out. So these 2 points do not exclude the possibility that the agent should have its own capacities and resources. So computational, syntactical, procedural, perceptual, everything you want in that sense, but that can be exploited through algorithms, through sensors and actuators to be able to ground its symbols. So together, these 3 points specify the zero semantical commitment condition, or the Z condition for short. So no innatism, no externalism, but you do allow, capacities and resources to be available to the agent. So any approach that breaches these conditions, or the Z condition as a whole, is said to be semantically committed, and thus will fail to solve the symbol grounding problem. This is what we're going to see throughout the different approaches that have been proposed. So I've been promising philosophy to pop up here. I think we've already seen a little bit of philosophy with the Chinese room argument, but philosophy is a field of study that is concerned with fundamental issues. Really, as I said before, it's the mother of all knowledge endeavors in science. So it's concerned with knowledge, reality, and existence. This may seem to be really far removed from CS, but when we see issues like these, like the symbol grounding problem, there are some pretty basic questions that jump up immediately, and we're suddenly in the realm of philosophy. So given that philosophy really studies a lot of different things, it's natural for different views, opinions, and outlooks to emerge. It's not math at all. So it's a social science. So there are different schools of thought, or intellectual traditions, or simply isms that come up and will come up in the papers that this lecture is based on. Some well-known examples of these isms are idealism, dualism, materialism, empiricism, rationalism. All of these isms are kind of ways to refer to a bunch of ideas that are grouped as schools of thought. Epistemology is one of the branches of philosophy concerned with knowledge, with the study of knowledge itself. And throughout history, there have been many views, more like thousands of years of study of this kind of thing. So we have different philosophers, like we see here, Plato, Locke, Kant, and Russell. They each focused on different things, Plato on what it is to know and how knowledge is good for the knower, or Locke focused on operations, Kant on conditions of the possibility of human understanding, and Russell on sensory experience. So I'm naming just a few of these philosophers because they come up. There's Heidegger also, who will come up in our discussions. They are referred to in reference to their views. So it's quite easy to come across things like the Kantian view or the Lockean view or Plato's cave metaphor, and that kind of thing already conveys a lot of thought put into these basic issues. So that's why in discussions they sometimes come up. All right, with this introduction in place, let's begin with the different approaches that have been proposed towards solving the symbol grounding problem. The first group is based on a representationalist approach, and RA for short. The representationalist approach considers the conceptual and categorical representations elaborated by an agent. So these conceptions and categories are considered to be innately tied to the meanings of the symbols used by that agent. So these strategies seek to solve the symbol grounding problem by grounding an agent's symbols in the representation that arises from the manipulations of the perceptual data. A little bit more specifically, it is usually argued that an agent is, or at least should be able to, capture at least some salient features shared by sets of data, abstract them from the data sets, identify abstractions as the contents of categorical and conceptual representations, and then use these representations to ground symbols. We're going to see a couple of more concrete examples, so this is more clear. The main problem with this set of approaches, as we will see, is that the available representations, whether they be categorical or perceptual, succeed in grounding the symbols. They do succeed, but only at the price of what is, usually referred to in philosophy as begging the question, which is somehow either saying you're not answering the question or you're actually assuming that something essential is already solved. So the elaboration of these representations and the availability of them presupposes precisely those semantic capacities or resources that the approach is trying to show to be evolvable. So this is what begging the question refers to. And Harnad, in his paper, proposes a strategy via which the symbols manipulated by an agent can be grounded by connecting to the perceptual data that they denote. And the connection is established, this is a pretty common way of thinking about it, in a bottom-up fashion. Nowadays, this would be sort of like a deep learning or a machine learning approach, where you start with the data and then you do some processing of these sensor motor signals. So his process works essentially in three stages. The first one, iconization, is the process of transforming analog signals. So analog means, the patterns of sensory data perceived in relation to a specific entity. So imagine just taking a picture or recording audio into iconic representations. So internal analog equivalents of the projections of distal objects on the agent's sensory surfaces. So when I say take a picture, what does that mean? It means that photons traverse space, they reached the sensor, the digital camera's sensor, and they formed a new signal, which is digitalized and is now a digital picture of my object. So it's really, this is what I mean by bottom up, right? So we're really at the physical level of capturing data. Then we have discrimination, the process of judging whether two inputs are the same or if they're different, how much they differ. So if I take a picture of Leo Messi, take one and then another in a different pose, I have to be able to discriminate if I'm really perceiving the same player or if it's just another guy, right? And then identifying is the process of assigning a unique response or a name to a class of inputs and treating them as equivalent or invariant in some respect. This is where the symbol emerges, right? Leo Messi is now the symbol that I apply to all manifestations of this person, this player, on my sensory surfaces. So the first two stages that we see are subsymbolic in nature, and the third grounds the symbol. So this is where the symbol emerges. So the iconic representations are obtained from the set of all the experiences related to the perceptions of the same type of object. So the categorical representations are then achieved through the second process, the discrimination process, where the agent considers only the invariant features of the iconic representations. This is where we realize that we're looking at the same player in different poses, right? And once elaborated, these categorical representations are associated with classes of symbols, the names that I was referring to. So I have a name for each player. Maybe I can leverage the fact that they're wearing jerseys and they have numbers on them, that kind of thing, thus providing appropriate reference, a reference that grounds them. And the approach attempts to overcome the typical limits that are encountered by combining both camps, right? The symbolic and the connectionist systems, by combining their strengths. But unfortunately, we'll see that this does not satisfy our basic condition for the problem to be solved. The problem is really rooted in the way in which the hybrid system is supposed to find these invariant features. So let's consider an agent following, again, Tadeo, called perc, perc for perceptor, or perceiver, or something like that. So initially, perc has no semantic contents or resources, so it has no semantical commitment. It's doing fine at the beginning. It is equipped with a digital video camera, as I mentioned before, through which it observes everything that goes around the environment. And so suppose that by means of the camera, neural networks, subsymbolic systems, perc is able to produce iconic representations from the perceptual data that it collects from the environment. This is our goal, right? It's then supposed to develop categorical representations from the perceptual data by considering only the invariant features. And next, it is supposed to organize the representations into conceptual categories. So something like this, like quadruped animal. And these are the meanings of the symbols, right? Or identify a player, as I was saying before. But the question is, where do these conceptual categories come from? So where does quadruped animal come from? Or where does Leo Messi come from? So neural networks can certainly be used to find structures in the data space, but if they are supervised, so something like backpropagation, we have some sort of loss function. They're trained by means of a pre-selected training set and repeated feedback. So whatever grounding they can provide is entirely extrinsic. This is the helping hand that I was referring to at the beginning of the lecture. If this were something that is unsupervised or semi-supervised or something like that, or let's consider the fully unsupervised case, then the networks implementing the training algorithms that do not use desired output data but still need to have built-in biases and feature detectors to reach the desired output. So the semantic resources are necessarily hard-coded. So it's not, it's even worse in a sense, right? It's hard-coded by a supervisor according to some pre-established criteria. So in our example, quadruped animal as a category is not really the outcome of perc's intrinsic grounding capabilities, because perc already has had quite a lot of semantic help to reach that conclusion. And therefore, really, this is not a solution to the problem. So this discussion, if you want to really get philosophical, is germane to the origin of natural language. So it clearly depends on the emergence of categories, right? It's fun, at least for me, to think about how natural language started out, thousands of years ago. There's study of this proposed by Cangellosi and others that have two methods via which they hypothesize that new categories may arise, and they call it sensor motor toil. So all the work that goes on in the organisms that experiment with direct perception and the result of producing categories for individuals. And then what they call is a pretty fun name, symbolic theft, is once these categories pop up, there's a process of stealing by hearsay that occurs, and the best categories win out. So this is a pretty reasonable way of thinking about how things occurred throughout a lot of time. But unfortunately, for us at least, the crucial issue of how natural organisms might learn to semanticize data from direct experience remains unsolved. So this really has no direct connection with the way artificial agents are doing it, and we'll see that this comes up again in one or two of the other proposals. So two more representationalist attempts before moving on. Mayo in 2003 suggests a functional model of agents that overcome some of the difficulties of the basic hard-nod hybrid model. And this may be interpreted as somehow addressing this objection that we proposed, that an agent fails to elaborate its own semantic categories. So the proposal by Mayo is that a functional organization of the representation as a way to ground symbols involved. So categories are interpreted as task specific. So let's relieve them of having to actually be there already. So they're going to be task specific that collect according to their practical function. Symbols are formed to solve the specific task-oriented problems in particular environments. So having a specific task provides the agent with some sort of bias that orients the search for the best categorization. And the bias is such that the symbols learned are those that most help the agents to perform the task successfully. This is, sounds pretty good, if you ask me. So the goal is to show that the agent could elaborate concepts in such a way as to be able to ground even abstract things, abstract concepts. So the agent perceives some continuum of sensory data, but one issue that comes up immediately is that data always underdetermine their structure. So it doesn't matter how much data you collect, there's always a countless variety of possible categories, including for specific tasks by means of which data could be organized. So Mayo acknowledges that without some sort of bias, it is computationally intractable to come up with the best set of categories describing the world. Given that sensory data is continuous, there is an effectively infinite number of possible categorizations of the data. So contrary to the hybrid model that we saw first, the functional model avoids the problem concerning the elaboration of abstract concepts. But like the other hypotheses in this group, the representationalist group, Mayo's also is founded on the elaboration of the semantics on categorical and symbolic representations. So the initial presence of these representations requires the presence of some substantial semantic capacities that cannot simply be warranted, again, without begging the question. And in Mayo's case, these are the functional criteria. So the fact that you can say that one is that is task specific, and whatever is helping you out for the specific task really is that's where the begging the question comes in. There's one more representationalist approach based on a different concept, that is the intentional model proposed by Sun in the year 2000, which relates connectionism symbolic representation, and situated AI. Situated AI is basically what goes on in specific environments, physical environments. So intentionality is a philosophical concept that has to do with directedness or aboutness, or a reference to mental states. So the fact that you're thinking about something is what's called intentionality. Sun refers to the interaction between an agent and the environment in, as I said before, Heideggerian terms of being in the world and being with the world. So these are two concepts that Heidegger develops as essential to the relationship of actually the existentialist conditions. So there's no, it's kind of like in contraposition with Descartes, who said that, you know, I think, therefore I am. No, Heidegger says you have to be in the world and with others in the world. So there's a situatedness that is necessary for existence to actually occur. And so Sun says the ability to elaborate the representations presupposes the more basic comportment of the agent with the world. So the agent is in the world and interacts with objects and other agents to achieve its goals. And the intentional stance is defined in the Heideggerian term of being with things. So the relationship with others is what makes existence possible. So according, again, to this view, representations do not stand for the corresponding perceived objects, but for the uses, so the aboutness that an agent can make of these objects as means to ends. So in that sense, it's similar to the functional proposal. There are two levels of learning proposed here. A first level that guides the behavior of the agent by considering the structure and the innate biases or built-in constraints. And the second, where the agent derives the best possible behavior according to some parameters. So unfortunately, you can see that already at the first level, our Z condition is breached, and therefore this is not an adequate solution to the symbol grounding problem. This is the same sort of issue that we ran into with the first couple of proposals. So this structure in the world and the innate biases, they're already begging the question. So moving on to the semi-representationalist approach, where we see that having failed to stay at the abstract level, like these three proposals that we analyzed just now, we're going to move on a little bit closer to perception. So there are three other strategies here developed by several authors throughout the years, especially in the 90s and the early 2000s, that though they're still representationalist in nature, they deal with the agent's use by relying on principles of behavior-based robotics. That's why I was saying that we're going to get closer to the physical world. The first model is epistemological. So remember, epistemology is the study of what it is to know. And the first one is by Davidson here in 95, who argued that the concepts must be acquired in some sort of gradual fashion as the agent interacts with the environment. Agents must be capable of incremental learning so that data can be categorized into concepts. Kind of what we were referring to as with the natural organisms developing natural language. And the conclusion is that neural networks are not adequate for this because they have a fixed structure. So there's the fixed nature of neural networks precludes this ability from really emerging. And again, remember, neural networks, 1995, they were already quite present. So Davidson says, a concept is represented by a composite description consisting of several components. So concept must be some complete description of its referent object, and it should thus collect different kinds of representations, one for each purpose for which the object representation can be used. So with a little bit more detail, there are three parts of a description that Davidson defines. The designator, so the name, the symbol used to refer to the object. The epistemological representation, so that is used to recognize instances of the category. So this is already the kind of the iconic representation that Harnad had. And the inferential representation, this is kind of the encyclopedic knowledge that we have and can be used to make further predictions or infer non-perceptual information, all the surrounding understanding that the agent has of this concept. So an example, a concrete example, the concept corresponding to the word or the symbol window could denote some 3D object model of a typical window and work as some sort of epistemological representation. When I say window, you immediately visualize some sort of structure that basically what it looks like or what it might look like in its different manifestations. The inferential knowledge component could then include information, kind of like what we saw at the beginning with the soccer knowledge base. Windows are made of wood and glass. They are used, so their function is to admit light and air in a building. They're fitted with casements or sashes containing transparent material like glass or certain forms of plastic or others, capable of being open and shut, usually, not always, and so on and so forth. So representations that ground symbols should not be pre-programmed, but rather learned, of course, otherwise we would be begging the question. So this has to arise from an agent's own experience. And Davidson suggests that using two paradigms typical of machine learning is in order here. So learning by observation and learning from examples. But here we immediately run into the same problems as before. So learning by observation, humans must provide the system with a specific number of well-selected description entities. So I have to tell you, learn by observation what a window actually is. This allows the agent to group entities into categories. Or even if it's an unsupervised learning algorithm, like a clustering algorithm, you're still giving it the underlying tools that will allow it to succeed. Learning from examples, in this case, the external criteria is even more clear, right? The sort of learning in question presupposes some pre-classified, labeled examples of the categories to be acquired. So Vogt in early 2000s connects the solution proposed early on by Harnad, the first one that we saw, with situated robotics. There's a pretty famous architecture by Brooks from the early 90s, and with a semiotic definition of symbols. So semiotics is the study of symbols, and this goes back even farther back. So from mid 20th century. So the strategy here consists in approaching the symbol grounding problem from the vantage point of embodied cognitive science. So we are going to ground the symbolic system of the agent in its sensor motor activity. So in the environment. We transform the symbol grounding problem into the physical symbol grounding problem, so the pH SGP, and then solve this problem by relying on two conceptual tools, which Vogt called the semiotic symbol systems and the guessing game. So Vogt defines the symbols used by the agent as a structural pair of sensor motor activities and environmental data. And according to the semiotic definition here he relies on Peirce's studies. We have a form, what Peirce called the representamen, the physical shape taken by the actual sign, so the scratch on the paper or the hole in the sheet. A meaning, or Peirce's interpretant, the semantic content of the sign, so what it really is meaning here, what it's referring to, how it should be interpreted. And what it's referring to is the third thing, Peirce's object. So the object to which the sign offers. So we see that here we have the three types of points of view that we have to consider in a symbol. So armed with this definition, Vogt intends to show that the symbols are already semantically grounded because of their intrinsic nature. So since both the meaning and the referent already embedded in the definition of a symbol, it turns out that to be direct, the latter turns out to be directly related to the object to which it refers and to carry the corresponding categorical representation. So the grounding of the whole symbol system is then left to special kinds of agents that are able to ground the meaning with their sensory-motor activities, thus solving the physical symbol grounding problem. That this is essentially the strategy proposed by Vogt. And the solution to the physical symbol grounding problem is then based on this second aspect, which is called the guessing game, which was proposed even earlier by Vogt and his co-author Steels, which will come up again a little later. It is basically a technique used to study the development of a common language by situated robots. So the game, this guessing game, involves two, or in general more, but at least two robots situated in a common environment. Each robot has a role where the speaker names the objects it perceives, and the hearer has the task of finding the objects named by the speaker by trial and error. In this case, we can imagine trying to teach a child or an animal, a pet, bring me such toy, or tell me what's that called. During the game, the robots develop a common system of semiotic symbol through communicative interactions, and they adapt. So they have this language that adapts. And keep in mind that the robots can only interact with the environment visually in this case. So the speaker communicates only to convey the name of a visually detected referent, and the hearer communicates only to inform the speaker about its guessing concerning the referent named by the speaker. And the guessing game ends successfully if the two robots develop shared lexicon, so grounded in the interactions among themselves and with the environment. This has actually been implemented and has been shown to be possible. So it's not as abstract as it might seem at first. So here's a visual representation of everything I just said. We have utterances, the speaker and the hearer, trying to come up with some shared way of pairing referents and utterances with meanings in their interpretation. So the game has essentially 4 stages, at the end of which the robots are expected to obtain these shared names. So the first 2 stages, they have the perceptual activities of the 2 robots and the selection of one part of the environment on which they will operate. This is not that important. The most important part is the last 2 stages, which concern the processes of meaning formation. So this is the actual goal. The discrimination game, through which the categories are elaborated, and the naming game, through which the categories are named. So the agents communicate to indicate the objects they categorized, and the speaker makes the utterance that works as the name of one of the categories that it has elaborated, and the hearer tries to interpret the utterance and to associate it with at least one of the categories that it has elaborated on its own. So there's like an alignment trying to happen here. So the 2 main difficulties with this strategy are that the semiotic approach assumes that the agent already has a semantics for the vocabulary being used. So an agent cannot be assumed to qualify as an interpreter without really begging the question. And the other relates to what the guessing game actually proves, even if it were successful. So the game cannot and really is not meant to ground the symbols. And it assumes that the agents manipulate previously grounded symbols to show how they can come to make explicit and share the same grounded vocabulary. So it's kind of missing the point, according to this analysis, where, coming back to the Chinese room argument, multiplying the number of people who need to learn Chinese as their first language by using only a Chinese dictionary does not really make things any better. This is I like this simple analysis. And this also brings us back to the origin of language. But really, the problem here is that we cannot assume that robots have human capacities. So in the case of a newly born child, there is cognitive science that has a hypothesis called the paucity of stimulus hypothesis. That means that there has to be something already there when we're born, involved into the structure of the brain that we have as soon as we're born, because there's such little number of stimuli in terms of language, and we start speaking, after only a few months or years or whatever, however long it takes you to learn to speak, that there has to be some sort of semantical commitment even in us. So we cannot assume that robots have human capacities. The third model is by Rosenstein and Cohen in the late 1990s, through another bottom-up process from percepts to symbolic thought and language. So unlike the others, their strategy is based on three components. So first, a method for organization of the perceptual data called the method of delays, or the delay space embedding, which allows the agents to store perceptual data without using any extrinsic criteria. It starts to avoid the problems that we ran into from before. Then we have a predictive semantics, and then an unsupervised learning process that allows the elaboration of some autonomous semantics. So it seems like it's going to work, right? So the scenario that we have is Ross, an agent that can move around in a lab, provided with sensors through which it can perceive, again, the environment as usual. Ross is able to assess distance, for instance, between itself and objects. So it's trying to avoid, bumping into stuff. And it registers distances at a regular time interval and plots distance and time values on a time-distance Cartesian coordinate system. All of this sounds, pretty intuitive, pretty basic. So suppose now that Ross encounters an object and it doesn't know whether it's approaching the object. It's just senses something through its sensorial perceptions, and it registers that at time t, Ross is at whatever distance from the object, and at t+1 it is a little farther from the object, so forth. So from this, Ross can deduce that it is moving away, because the distance increased. So we can plot things like this. We can develop things like escape, like chase, come into contact. So populations of agents like Ross can interact and adopt strategies for pursuit and avoidance and that kind of thing based on how effective they are. So imagine a learning system that can learn to chase, and it'll learn to behave optimally, in the sense that it'll, in a kind of like a reinforcement learning scenario where you just choose your actions in the best possible manner based on this reward function. So it seems that the symbol grounding problem here is solved without using any external or pre-semantical criteria. But if you think about it, the Cartesian coordinate system, so the plotting procedures, the symbolic conventions used by the agent, really constitute a pivotal semantic framework, allowing the elaboration of an initial semantics by the agent. So this Cartesian semantic framework is entirely extraneous to the agent. It didn't come up on its own. So it either was presumed to be there, so that would be a violation through innatism, or even more realistically, having been superimposed by the robot's programs. So the very interpretation of the data provided by the actions is by itself a crucial semantic step based on extrinsic criteria, and thus we are again in the presence of a failure to solve the symbolic, a symbol grounding problem. So the first two approaches didn't work for various reasons. Let's see if totally eliminating representationalism, let's see if that works. So the physical grounding hypothesis, the roots of the non-representationalist approach, it can be, the roots may be dated to the criticisms made by Brooks, as I mentioned earlier, who developed a pretty well-known architecture of the classic concept of representation. So he argues that intelligent behavior can be the outcome of interactions between embodied, situated agents, robots, and so the symbolic representations are not necessary. All we need are sensor-motor couplings. So this is what Brooks called in 1991 the physical grounding hypothesis. The argument being that if there is no symbolical representations to ground, then there is no symbol grounding problem to be solved. It's like, let's just get rid of it, right? So in the late 80s, early 90s, Brooks developed what was well-known subsumption architecture for controlling mobile robots. So the novelty in that time was that the different types of tasks that needed to be done were decomposed into asynchronous modules that ranged from the very concrete things like avoid objects to the more abstract like identification, planning, and reasoning about behavior. So in this case, the problem is that the symbol grounding problem is really just postponed rather than avoided, because an agent implementing this model, this architecture, may not need to deal with the symbol grounding problem initially to deal successfully, but if it is to develop even an elementary proto-language, something that allows it to communicate with others and have higher cognitive capacities, it will need to manipulate some symbols. Some sort of symbolic manipulation must be, it will be required. But then the question of their semantic grounding will present itself again. It's just, that's why we say that it's nearly postponed. So this is the problem addressed in the following two strategies. And with that, we reached the 8 that we promised. So in 1999, these two authors, Billard and Doddenham, proposed a communication-based approach. So their focus was on social skills, learning, communicating, and imitating. And they investigate grounding and use through simulations of groups. So they have an experimental scenario with, in their case, 9 agents interacting in an environment with short-term memory, and their task is to learn a common language. Again, it's very similar to the guessing game that we had before. So the agents are expected to learn a vocabulary to differentiate between colored patches in their experiment, and to describe their locations in terms of distance and orientation relative to some home point. So the vocabulary, in their own words, transmitted from a teacher agent, which has a complete knowledge of the vocabulary from start, to 8 learner agents, which have no knowledge of the vocabulary. So there is an imitative strategy going on here, and from the teacher to the learners. And the grounding of the teacher signals in the learner's sensor actuator states results from an association process via some dynamic, recurrent associative memory. In this case, they call this the DRAMA, dynamic recurrent associative memory architecture. But there are several problems to this. You probably picked up on that if you were paying attention when I was just quoting the author. The learning agents are endowed with semantic resources whose presence is already presupposed. So this is already innatism. There is a reliance on neural networks, which incurs the same problems that we mentioned before. And the learning agents acquire a pre-established complete language from an external source, the externalism. They don't develop themselves. They're just learning it by interaction. So the external source teacher is merely assumed to have full knowledge of the language. And this is another form of innatism that is unjustified in connection with our problem. So finally, Brooks, Varshavskaya, and they both argue that the development of semantic capacities in an agent could be modeled on the development of linguistic capacities in children. Again, so this proposal supports some sort of pragmatic interpretation of language acquired in agents, whereby, quoting again the author, language is not viewed as a denotational symbolic system for reference to objects and relationships between them as much as a tool for communicating intentions. The utterance is a way to manipulate the environment through beliefs and actions of others. So language is just seen as some pragmatic interaction of the agent with its environment, and the semantics, therefore, does not need any representation, is the argument. So this, we don't have time to go into this, but this is kind of the model that they have of language and what the intentional and behavioral connections are there. And here you can see that the learning approach really is inadequate to deal with the symbol grounding problem successfully, because the origin of semantic capacities in agents cannot be addressed by, again, as we said before, referring to modalities that are really appropriate only to human agents. So in this case, in the case of human agents, we can assume that there's a natural and innate predisposition in the agent to acquire language, as I said before, with the cognitive sciences studies that proved somehow that this is already there. The existence of an already well-developed language. So we're not talking about the first ever human learning to speak with another one. We're just, learning. We're just referring to some newly born child in today's world where there's already a well-developed language and the presence of a community of speakers, all of us proficient in the language who can transmit the knowledge. So really none of these assumptions is justified. And therefore, this is also not an adequate solution to the problem. So we're running a little bit short on time. What I'm going to, we have basically two more things to talk about. The last almost 20 years since this 8 proposal review was published. We go over, a couple more. The same authors, Taddeo and Floridi, a couple of years later came up with what they called a practical solution to the symbol grounding problem, where here practical refers to the interactions that are information oriented. So their model is based on a theory of meaning called action-based semantics and a kind of agents called two-machine artificial agents, AM squared. We don't have time to go over this, but essentially the action-based semantics, the meanings of the symbols in the beginning are generated by the agents in internal states. So they really want to, come up with the symbols on their own, and they claim that the very first step of meaning is not in itself a semantic process because it's free of purpose. It assumes that the action performed and not the goal to be achieved is going to ground its symbols semantically. So even if an agent performs some action randomly or incorrectly, the action-based semantics still identifies that action as a source of the state and then provides the meaning of the related symbol. So semantics has the initial roots in the individual agent's behaviors and not the community. That's the trick, and that's the only thing I'm going to say about this. you have the two machine agents that have two levels. So you have the object level and the meta level, which will elaborate on that, and that will, allow it to have this causal coupling that will help this emerge. This is a specification of that. I'll leave it for offline analysis for you guys. And this, a few years later, there was an author in 2014, Bieleka, who published a paper titled "Why Taddeo and Floridi Did Not Solve the Symbol Grounding Problem." So she refers to an excessively liberal relationship between symbols and internal states, accusing them of not really being very precise, and the notion of action considered to be seriously defective in the theory due to the lack of possibility of symbols to misrepresent. So anything goes, basically. So this is useless. It is unclear why they would be grounded in the first place then. But however, she does mention that it is probably one of the best attempts so far to solve the symbol grounding problem. Again, this one, and now I'm almost done. In 2008, Steels, one of the authors that I mentioned a while back, published a paper saying that the symbol grounding problem has been solved. And he claims that, this is basically done with the guessing game setup that they developed, essentially saying that that's all that's needed. But in a few years later, also in the same years as the other one that I mentioned, this other Bringsjord responded to, in a quite short and interesting paper that I posted on Canvas, saying that the symbol grounding problem remains unsolved. And he states that unfortunately, the proposal, while certainly innovative, interesting, and giving the acute difficulty quite brave, merely shows that a class of robots can, in theory, connect. In some sense, the symbols it manipulates with the external world it perceives, and can, on the strength of that connection, communicate in some subhuman fashion. And that's basically it. So, some closing remarks. The desiderata that I promised by Taddeo and Floridi of what we need to solve the symbol grounding problem, all the requirements, and last slide, a little bit of food for thought. So it's been really shown this symbol grounding problem to be really a really difficult problem that has functional issues, that is tied to philosophical ones that are triggered by the desire to grasp the problem of consciousness. Here we only covered a few that are mostly related to Neuro Symbolic AI, and though much of this was philosophical in nature, I think it's interesting to address some concrete questions like, do large language models nowadays, do they know what they're talking about for autonomous driving? Do these systems really understand their environment? And concretely, in their current form, can these systems be engineered to fully, reliably avoid silly mistakes, be ethical, and that kind of thing? So sorry for going over a couple of minutes. That's the end of my lecture.